All right, let's talk about AI. We hear all the time how it's based on the human brain, right? But what if that whole comparison is just wrong? What if we've been trying to copy the wrong thing all along? Today we're going to dig into a really cool idea that flips the script on how we think about machine intelligence, and it all starts with the possibility that we're copying the wrong part of the brain entirely.
So this quote really kicks things off. We usually think of intelligence as, well, this fuzzy kind of magical thing. But what if it's not? What if it's just a process? A really complex one, for sure, but still a process. Something you can actually define and measure and, most importantly, replicate the right way. And if that's true, well, that changes everything. Because it means there's a right way and a profoundly wrong way to build it.
Okay, so that brings us to the first big idea. The problem might actually be hiding in plain sight, right there in the name, artificial intelligence. See, when we say something is artificial, we're usually talking about a copy of an item, but intelligence isn't an item at all.
Think about it this way. An artificial hip, right? That's a copy of a physical object. Simple. But intelligence? That's not an object you can hold. It's a living, breathing process. And this is where the source material says we're going off the rails. We're so focused on copying the item, the single neuron, and turning it into code that we're completely missing the brain's incredible dynamic process of learning and connecting. And believe me, that one little mix-up has massive consequences.
And one of the first, and honestly most shocking consequences, is energy. Our brains are just unbelievably efficient. The computers trying to copy them? Not so much. Let's get into why that is.
Okay, so it really comes down to how they handle information. Digital systems are binary. It's all ones and zeros. Think of it like a light switch. It's either on or it's off. To do anything complex, you have to flip millions of those switches, and every single flip costs energy. But the brain, it's analog. It's way more like a dimmer switch, It has all these different levels in between. That makes it wildly efficient. A biological neuron is just built to be low energy. The difference is huge.
And this number right here, this is where things get really serious. This isn't just a technical problem, this is a physics problem. That number is the absolute rock-bottom, non-negotiable amount of energy it takes to erase one single bit of digital information. It's a fundamental law of the universe. So every single time a digital model learns something or changes its mind, it has to pay this energy tax. A tax that our brain, our biological brain, doesn't even know exists.
But look, it's not just about energy. The difference is way deeper than that. It's architectural. It's about how the networks are actually built. Are we talking about a fixed blueprint or a living, growing thing? That's really the question here.
And this table really gets to the heart of it. A biological neuron is alive. Its little output arms, the axons, are constantly out there exploring, actively looking for new things to connect to. When your brain learns, it's literally, physically, rewiring itself. Now compare that to an artificial neuron. It's static. All its connections are decided at the very beginning. So when it learns, all it's doing is turning up or down the volume on connections that are already there. It's the difference between building a whole new highway versus just changing the speed limit on an old road.
So this whole searching thing that real neurons do, what exactly is it? And why does it matter so much? Well, according to the thinking here, this is the one crucial piece of the puzzle that today's AI is completely missing.
Okay, this is the magic sauce right here. Axon searching. It's the brain's superpower. It's the ability to physically grow new connections, to seek out new pathways whenever it hits a problem or needs to learn. Again, it's not just making the old roads better, it's literally building brand new highways for information. This is how our brain grows, how it gets more powerful over our lifetime.
So you're probably thinking, how on earth could you get a computer to do that? Well, the author has a really clever idea. What if we could teach an AI to use a tool it's already an expert at, searching the internet, to act like a biological neuron? Just picture it. The AI realizes there's something it doesn't know, a gap in its knowledge. So it actively goes out, searches for the information, finds a good source, basically a new neuron out there on the web, and then creates a permanent link to it. It would be teaching itself how to grow, how to upgrade its own brain. That's not just an improvement, that's a total game changer. Okay, so let's follow that thought. If we could actually build an AI that doesn't just learn facts, but learns how to make new connections, what happens then? The possibilities are just staggering. We're talking about a whole new future for AI. And here it is, the ultimate payoff. The argument is that this dynamic, this constant searching and connecting, that is the secret. That's how a brain goes from just being pretty smart to becoming something truly expansive, maybe even a superintelligence that can keep adding to itself, keep growing. We're not just talking about an AI that knows more facts, we're talking about an AI that fundamentally expands its ability to understand everything.
So that leaves us with a really big question, doesn't it? For so long, the race in AI has been about more data, bigger models, more computing power. But what if that's not the answer? What if the next giant leap for AI isn't about making it bigger, but about teaching it to make better connections? What if the future is about an AI that doesn't just think, but can actively reach out and grow on its own? It's a pretty wild thought to chew on. Thanks for sticking with me on this one.